Hi everyone, my name is Mariana, and today I'm going to tell you about the falling cat problem. You may have heard about Schrodinger's cat in quantum mechanics, but this is different. I will look at the classical problem of a falling cat. To get started, let's talk about conservation of momentum. We talk a lot about conservation of momentum in 130, so this is a very familiar idea to you all. Take the example of a game of pool. When a moving pool ball hits a stationary pool ball, the two travel off with their own velocities. However, the total momentum of the system of the pool balls is conserved. The total momentum before the collision is equal to the total momentum after the collision. Now that we're familiar with conservation of momentum, let's talk about a more complicated example, the falling cat problem. You have probably heard that cats seem to always land on their feet, even when they're dropped starting upside down. This phenomenon fascinated physicists, including George Gabriel Stokes and James Clerk Maxwell, for reasons we'll get into in a second. Physicists are still talking about falling cats today. Take this article from the Washington Post, for example. In the falling cat problem, the cat is initially held upside down in the air. Since the cat is at rest, we can say that it has zero net momentum. When the cat is dropped, it naturally wants to land on its feet. To do so, the cat rotates itself around 180 degrees. However, let's think about this in the context of conservation of momentum. It appears that the cat is going from having no momentum, when it's held at rest, to having some angular momentum as it rotates in midair. Is the cat's angular momentum being conserved? Does this example break the law of conservation of momentum? Questions like these got physicists like us thinking. Let's look into this problem more. What's important about the falling cat problem is that the cat is a non-rigid body. That means that the cat is able to pivot about its center of mass. It can spin its head and its tail independently. Clearly, this complicates our analysis. To better understand this motion, let's cut the cat in half, but not literally. Let's consider the angular momentum for the various components of the cat. For the cat's local axes, it has an angular momentum associated with its head and its tail. We know that angular momentum is equal to the moment of inertia times the angular velocity, or the radius crossed with the momentum. First, let's look at the motion of the cat's head. Using the right-hand rule, we curl our fingers in the direction of the rotation, and our thumb points in the direction of the resulting angular momentum. We can see that the angular momentum associated with the rotation of the cat's head points into the page, towards the cat's face. Now, let's look at the cat's tail. Using the right-hand rule, we curl our fingers in the direction of the rotation, and we see that the resulting angular momentum points out of the page, away from the cat's tail. Now we have two components of the cat's angular momentum. However, there is one component that we are still missing. When we break down the motion of the cat, not only is the cat's head and tail rotating about the cat's center of mass, but the cat's entire body is rotating as well. So, we must take into account the angular momentum associated with the rotation of the cat's center of mass. Now, we have all the components of the cat's angular momentum. That associated with the rotation of the head, the rotation of the tail, and the rotation of the center of mass. When we add these three components together, we see that the net angular momentum of the system at any given moment equals zero. Since there are no external torques acting on the cat, it must have net zero angular momentum all the time. We can see this reflected in the momentum principle, when the change in angular momentum equals torque times the change in time. This agrees with the analysis we just showed. So, indeed, angular momentum is conserved in the case of the falling cat. Physics isn't broken after all. This tendency of cats to always land on their feet, also called the cat writing reflex, is cool and all, but why do scientists care so much about it? Well, it turns out that scientists have a lot to learn from this reflex. In 2015, researchers from Mumbai, India, published a paper on how the cat writing reflex, also called the CRR, can apply to robotics. These researchers see applications of the CRR in self-orientation of satellites and human motion control in zero gravity. The goal of their study was to analyze how their practical model of the CRR compared to the theoretical model proposed by Kane and Schur in 1969. They developed a practical simulation of the falling cat using MATLAB and a software called SimMechanics. Here are timeframes of the position of the cat at certain moments during its fall, according to their practical model. In the end, the researchers found that their simulated model predicts the motion of the cat with considerable accuracy. So, not only is the falling cat problem an interesting phenomenon to study, but it also inspires new designs in robotics. Thank you all for taking the time to watch this video. Hopefully you see that the falling cat problem is just one example of many fun physics problems that are in your future. Good luck!